K-polytopes is a generalization or rather a superproblem of k-means formulated through sparse representations. Here, the outline of this presentation is given. First, we will make an introduction to clustering and then tie it with sparse representations through block sparsity. A geometric perspective of this process will also be given arriving at k-simplexes and k-polytopes formulations. Then preliminary results will be mentioned along with a discussion of this methodology. Clustering is an unsupervised learning method where no labels are needed. It aims at grouping entities in terms of their similarity. In the most conventional setting, a small Euclidean distance between two entities signals to their similarity. Note that, the results will crucially depend on the similarity notion adopted. Clustering methods can be categorized based on the models they learn. K-means is the most well-known prototype-based formulation. There are various other methods that learn graphical, hierarchical, or distributional models. K-polytopes is in fact an amalgamation of all these methods, but is based mostly on a prototype-based approach. On the left you can find K-means in action. Each prototype is a central point responsible for the cluster it claims, collectively minimizing the Euclidean distance to all points. In K-lines on the right, lines are chosen as central objects. This way, an infinitely many number of central points can be utilized, in other words prototypes are now dimensional. This logic can be extended to higher dimensions, arriving at K-planes, or K-flats in the most general setting, where a flat is a generalization of a line or a plane to higher dimensions. Most importantly, K-means and K-flats are of the form of sparse representations with certain constraints imposed. In sparse representations, each data point yi is expressed through a linear combination of a few vectors chosen from a redundant set. A few vectors can only be used and this is imposed through the L0 constraint, namely at most q number of vectors can be used. Xi is then the sparse representation of the data point yi, and the non-zero entries in Xi correspond to coefficients of those few vectors chosen. At the time of this presentation, there has been no efficient way of solving this highly non-convex optimization problem, and it is known to be NP-hard. An approximate procedure is as follows: first fix A and solve for Xi, this corresponds to sparse coding step. Then fix all Xi and solve for A, namely the dictionary update. And iterate between until convergence. Importantly, the vectors, or the columns or more technically the atoms need to be normalized. There is no structural constraint on the code patterns and conventional representations. Through structured sparsity group or block patterns can be imposed on sparse vectors. A single block is allowed to be non-zero in block sparsity setting. Here is the mathematical formulation of block sparsity setting. A. K designates the kth subdictionary. K star indicates the optimal subdictionary for data point yi. The final constraint ensures block sparsity. A subdictionary in fact behaves like a central prototype claiming identity, or not, based on the reconstruction error, much like a centroid claiming the closest points. Dictionary update then corresponds to updating the central prototypes. K-means can in fact be formulated within a sparse representations framework as depicted. When Xi, for all I, has only one non-zero entity and that can only be value 1, then it is a direct formulation of K-means. Rest of this presentation is on novel formulations building on top of K-means. K-simplexes will be formulated as a higher order generalization of K-means and also will further be developed into K-polytopes to model arbitrary numeric datasets. A geometric perspective will now be given that will build towards K-simplexes. Let us consider two vectors A and B in Rn. These two vectors span a subspace, namely a plane crossing the origin in the depicted case. Given the expression, or rather with some to one constraint, they now trace a line within that subspace. Furthermore, with positivity constraint we now arrive at a line segment within that line. We can now rewrite these expressions in matrix form to connect them to sparse representations. First with sum to one constraint and then further with positivity constraint, as follows. Now consider three vectors case in Rn. We will then have a 3D space crossing origin, an arbitrary plane, and finally an arbitrary triangle, respectively. In the most general case, with Q vectors, we will then have a Q subspace, Q-1 flat, and a Q-1 simplex. Assuming block sparsity on top, we then arrive at clustering formulations of each geometric entity. Here is a summary of this geometric roadmap given through a table of constraints. Strikingly, K-simplexes appear to be the most consistent generalization of K-means. Mathematical formulation of K-simplexes can be given as follows, in the block sparse setting, with additional sum to 1 and positivity constraints on the sparse coefficients. In solution to K-simplexes, projection onto the closest subspace is now replaced with projection on the closest simplex. Note that, for a given data distribution there will be infinitely many best fit simplexes. Best fit simplexes may not be apparent solutions to the clustering problem. A solution is to add an additional term that will penalize the size of the simplexes, but then the problem will turn into a multi-objective one. Solution chosen here is to limit the size of simplexes. Tau now denotes the maximum allowed edge size of a simplex. Moreover, simplexes are convex structures. It is highly desired to have prototypes of non-convex shapes. Therefore, further generalization of K-simplexes is needed and is attained by K-polytopes. This study sticks with the definition that a polytope is an intact object that admits an exact simplicial decomposition. For example, a polygon, a two-dimensional polytope, always admits a triangulation. Then in general terms, a polytope is a connected composition of many simplexes. Now, within a polytope there are p choose q+1 simplexes to test for assuming that a polytope has p vertices. Therefore, an additional structure namely HK, a hypergraph is kept for each polytope. An important observation is that HK refers to a connected hypergraph. HK indexes AK and each entry refers to a valid simplex. Vertices are abstracted out as nodes of the hypergraph and each valid simplex corresponds to a hyperedge that relates Q+1 nodes. If HK is not connected, it means there are actually two or more polytopes defined over AK, contradicting the hypothesis of K-many polytopes to start with. There is another observation to be made. Namely, although a simplex is valid within a polytope, it may not receive any projections, exhibiting redundancy. Therefore, as an additional constraint, each simplex should claim at least lambda many data points. Here is the final formulation of K-polytopes. Initializing the system with K-many random polytopes will not be an effective strategy. The proposed algorithm starts with a single random Q-dimensional simplex, which gradually evolves into K-many meaningful polytopes. There are two main problems. The initial random simplex is, most probably, not structurally correct. Dictionary update step may introduce unevenly sized simplexes and some of these simplexes can become redundant. These can be addressed by an adaptive structured sparsity approach through subdivisions and pruning. In subdivisioning, if a simplex surpasses the edge size threshold tau, then subdivide it into two, adding more detail. In pruning, if a simplex is being rarely used or not used, eliminate it. Most importantly, this process is necessary for emergence of new prototypes. When enough simplexes are eliminated, the polytope will break into two or more. Note that, even with all these, the algorithm produces a structurally approximate solution. The resulting polytopes will only be grids of simplexes. Through an additional merging process, simplexes from different connected components can be stitched together depending on the parameter tau, allowing more general and flexible shapes rather than simplex grids only. Here is the family of clustering methods that can be attained through the framework presented here. K-polytelens and K-polygons as 1D and 2D prototypes are tested for experimental validation, in 2D and 3D data spaces respectively. Here are the convergence states for synthetic crescents and reduced hemness datasets. using one-dimensional polytopes. Here are some animated results on crescents and spirals datasets, to demonstrate how the process works. With the merging process involved, connected components then directly designate the clusters as depicted here. As final notes, this method might be a remedy for curse of dimensionality in many circumstances, but more efficient algorithms for high-dimensional cases are needed. As is, the method is capable of modeling nonlinearly distributed datasets. Most interestingly, it can be flexibly utilized in a supervised setting through one-class learning. Thanks for watching our presentation.